Hi everyone, this is the second lecture bite for week 3 of Astronomy 236. This lecture bite focuses on measuring astronomical speeds and velocities. So just a quick overview. Speed is distance divided by time. It's how far you can go in some period of time. So for example, I'm showing here a fellow standing on top of a car who is going to travel some distance. Over the course of about 5 seconds, and I timed it so it had to be 5 seconds, this guy travels 8.3 centimeters on the screen. So if I calculate his speed, that is the distance he traveled divided by the time it took him to get there. So that's about 1.66 centimeters per second. If instead he goes a little bit faster and travels the same distance in 1 second, now his speed is 8.3 centimeters per second. So it's pretty straightforward. A speed is just the amount of distance you can go in a certain amount of time. Now, I also want to draw a little bit of a comparison between speed and velocity. These are very similar terms, and they're often used interchangeably. But there's one main difference that astronomers and physicists think about when we decide whether we want to use the word speed or velocity, and that is what direction we're going in. So here's what I mean by that. So here's this fellow in the car again, and he's going to move quickly from point A to point B. He traveled 8.3 centimeters in 1 second, so his speed was 8.3 centimeters per second. His velocity was also 8.3 centimeters per second. Now I'm going to send him back the other way. This time, his distance was also 8.3 centimeters. His time also took 1 second, so his speed was still 8.3 centimeters per second. But now his velocity is negative, and that implies that he's going the opposite direction. So velocity is negative 8.3 centimeters per second. And this is something that we care about when we try to figure out where things are moving, because often we care just as much where they're going as how fast they're getting there. So one way that you can measure velocities of a thing in space is to measure how quickly an object changes its position over time. That's basically what we were doing with the guy on top of the car. We were seeing how fast his position changed over a certain period of time. So if we want to do this for astronomical objects, one of the things we need to be able to do is measure positions in astronomy. So I'm going to do a quick diversion and explain how we do that. And it's very similar to how we measure positions and places on the Earth. So on the Earth, we divide our Earth up into imaginary lines of latitude and longitude. Latitude tells us how far above the equator we are on the sphere that is Earth. And you can see a couple of them that I've labeled here. So this first line above, the first white line above the red line is 10 degrees north, or plus 10 degrees of latitude. If you count up a few more, you go up to 50 degrees north, or plus 50 degrees. We usually say that north is positive and south is negative, just because that's the way we've defined our coordinate systems. So if I were to go below the equator, I could go 20 degrees south, which would also be negative 20 degrees. Lines of longitude go the other way. So instead of slicing the Earth vertically, they slice it kind of like you would an orange, and they cut it up into different equal slices going around the Earth as the Earth spins. So this red line is the prime meridian. That is the line from which we measure all of the longitudes. It's a little bit arbitrary, unlike the equator, which is actually a very meaningful line, which is where the Earth spins about. We just chose a particular line to be the prime meridian, and we just measure everything based on that. So if you go 2 lines to the left of the prime meridian, that takes you to 20 degrees west. And if you go 7 lines left, that takes you to 70 degrees west. And you go all the way around to 360. So anywhere on Earth, I can specify with 2 numbers, the latitude and the longitude. If I chose this particular place right in the lake outside of the UW campus, that particular spot in the lake is given by these particular numbers: 43 degrees north, 43.078715 degrees north precisely, and 89 degrees west, 89.405252 degrees west. So anywhere on the Earth, we can specify coordinates with just those two numbers. And we can do this almost exactly the same way for objects in space as well. So here is the way we do it. We have this coordinate system of declination and right ascension, which is almost identical and almost exactly analogous to latitude and longitude. Declination is just like latitude. It goes up from the equator. We have the same equator in the sky as we do on the Earth. And positive declination is in the north, and negative declination is in the south. And we also have lines of right ascension. So the lines of right ascension are just like the lines of longitude. We arbitrarily choose a place that is right ascension 0, and we march around the sky. So each of these particular lines is incrementing by 40 degrees or so. So a right ascension of 40 degrees would be this line here, and a right ascension of 80 degrees would be this next one over. So now let's take this and let's put it into practice. We can specify for every single star its position with two numbers, the right ascension and the declination. So now let's look at a star that happens to be moving quickly. So this is an image taken in the 1950s of a part of sky. If I look at the same region of sky and an image taken 40 years later, you can see that one thing in particular has changed. Did you notice it? This star in the middle is moving, and you can see it, if I flip back and forth, jump from its old position kind of in the upper right corner, or closer to the upper right corner in 1950, to its newer position closer to center in the 1980s and the 1990s. So how do we take this change in position, this slight change in the right ascension and the declination of this star, and convert that into a speed, or more precisely into a velocity, because we care about what direction the star is traveling? So this star, which we call GJ 1214, travels about 0.01 degrees on the sky over 40 years. And the direction of its velocity is towards the southeast. Now, this is going to be a little bit tricky because in astronomy, we have east and west reversed. And the reason for this is that we are looking up towards the celestial sphere instead of down at it. So if you lay down and you pointed your head towards the northern hemisphere, and you tried to figure out which direction was west and which direction was east, it would be the opposite as if you were standing up and looking towards the ground. So even though on a map that we're used to looking at, west is typically to the left, in astronomy, when we look up at the sky, west is typically to the east. So this star is moving to the southeast. Now, there's a major problem here, which is that just based on how an object is moving on the sky doesn't mean we know exactly how far it is moving in physical numbers in real life. And the reason for this is our perspective. Closer objects move larger angles than distant objects when they're traveling at the same speed. So here I'm showing two fellows in a car, and they're going to travel at exactly the same speed, but one of them is twice as far away, this guy on top, and that's why he appears to be twice as small. So when we see them move, we can observe that the closer object moves further. It traverses a greater angle than the far away object does, even though in truth, they have both moved exactly the same distance. So we have a formula for how to relate this, and it's pretty straightforward. All you do is multiply the distance to the star that we talked about in our last lecture, which in this case we can measure with the parallax method. We can multiply that distance by the angle, and with a conversion factor, we can figure out how far that star is moving in real life. And then we can divide that amount of distance by the time it took for it to move that distance. So if I plug in these numbers for GJ 1214, I find that the star is 47 light years away. It's traveled 0.01 degrees over 40 years. That all converts to moving about 0.008 light years over that time, over 40 years. And if I convert that to units that are a little bit more familiar to us, that's about 65 kilometers per second. That is really fast. For comparison, a typical speed for a car is about 65 kilometers per hour. So this star is moving about 1,000 times faster than we would drive in a car. And it's moving that direction in the southeast. So this is all well and good. We now know how this star is moving, as we can tell in the plane of the sky. But what we can't tell is whether the star is moving towards us or away from us at all, because we're looking at a two-dimensional projection of that star's motion. We don't actually see the star getting closer or further from us. So how do we figure that out? How can we tell if the star is moving towards us into the screen or away from us out of the screen? So last time we talked about measuring distances with parallax. One thing you might think of is to measure the parallax of the star a couple of times and see how much it's changed, and see if the distance away from us, from Earth to the star, is changing over that amount of time. It turns out that this is actually not very easy to do. Parallax measurements are very difficult to make, and we just can't make it precise enough to see such a small distance unless we wanted to wait, thousands or millions of years to make this measurement. So instead, we turn to another trick, which is called the Doppler effect. So think back to your waves course and imagine that you're producing a wave. In this case, let's imagine that it's a sound wave. What is a wave but a series of peaks and valleys? We're representing these peaks and valleys here by these concentric circles, or these almost concentric circles. And these peaks and valleys, these black circles, imagine that they're the peaks. And when you move, and when you're standing still and you create sound, you produce a bunch of perfectly concentric peaks around where you are. But now imagine that you're moving forward. What you can notice is that in the time it takes for you to emit consecutive peaks, so in the maybe fraction of a second between the two black circles as they're emitted, your car is moving a non-negligible distance during that time. And what that means is that the peaks in the direction you're moving are a little bit closer together than they would have been, because you've moved closer to the last peak by the time you emit the next peak. So what you're essentially doing is you're changing the wavelength of your motion, of the wave. The wavelength in the direction that you're moving is shorter because you are moving too, and you're shortening that wavelength. Now, remember back to our lecture on waves and on light. These three properties are related for waves: the speed, the wavelength, and the frequency. So for waves like sound and light, we know that the speed is constant. The speed of sound doesn't really change. The speed of light doesn't change at all. So if the wavelength changes, the frequency must change as well. If the wavelength gets shorter, the frequency gets larger. And in sound, that means that the pitch of the sound becomes greater. So this is why when you see an ambulance or a police car going by and you hear its siren, you might hear the pitch of the siren change depending on whether it's moving towards you or away from you, like you'll see in this clip here. So as the fire truck moved towards you, you could hear that the pitch was high, and then as it started going the other direction, you could hear the pitch lower. This is exactly that effect. And it works for sound. It also works for light as well. Except in light, changing the wavelength and changing the frequency doesn't change the pitch. It changes the color that you see. So think back to our lecture on light, where we showed that the elements produce characteristic colors of light, which are determined by quantum mechanics, that are determined by the Schrödinger equation itself. What if you are emitting light from hydrogen atoms, but these hydrogen atoms are moving towards or away from us? What you'll get is you'll get a shift in the exact position of these lines. In particular, maybe this n equals 4 to n equals 2 line will become slightly redder if we see it in a source that's moving away from Earth. And if it's moving towards us, we'll see it get slightly bluer and show up at a slightly smaller wavelength. So this is how we can measure speeds of things moving towards or away from us. We look at their spectrum and we try to see if these lines, these fingerprints, are shifting slightly back and forth. And in some cases, you can use this to determine if there are things orbiting one another. So in this instance I'm showing here, a star with something orbiting it. And as the star and this other object orbit, it shifts the light back and forth, and it shifts the colors of these fingerprints, these dark bands in the spectrum shown at the bottom, back and forth. And you can use that to measure speed of this object over time. So the Doppler effect changes the color of light for moving objects. So now let's go back to our example star of GJ 1214. So if we want to know what direction or how GJ 1214 is moving towards us or away from us, all we have to do is take a spectrum and measure the brightness at all different colors. And you can see that there are lines in these spectra. And we can measure the positions of these lines and compare them to the positions of the lines that we know should be there from our knowledge of quantum mechanics and from the Schrödinger equation. And when we do this, we can find that GJ 1214 is moving away from us at about 21 kilometers per second. So wrapping back up, GJ 1214 is traveling towards the southeast at about 65 kilometers per second. And at the same time, it's moving away from us into the plane of the sky, into your screen, if you look at it this way, at about 20 kilometers per second. So really, its motion is an angle, slightly this way, away from us and down into the left on the screen.